Hello, this is the fourth video of mathematics for computer science. So, as we discussed last time, we did conclude an idea about what we have in mathematical findings that we discovered through the time. That's our fruit leverage that we can use whenever we're doing any design and computation for a reachability of a problem that we couldn't resolve in an ideal way or in a manageable way, time and way. And I want to apply this idea through the module that we discussed and or we read in this week, which is counting. So I want to apply this idea and reflect it on it so we just see a concrete way of it. So we're going to define counting here as the combination of operands or operations that grow through scale. So the more the scale, the more the operands on the operations that we're having. And we know that counting is very simple when the numbers are low and the scale is manageable through humans or machine. But once you make the scale is bigger through the scale of infinity, I mean, I'm not talking about infinite numbers here, but just trying to reference or represent high numbers or high scales, then the problem becomes unmanageable or impossible to an extent. So it is very hard to be resolved even with the humans, not only machines. And if it is resolved by machines, then it is resolvable with an efficient way or an unmanageable or inadequate way. So an example would be calculating something that could take 3 days or 1 month or 1 year. There is no point of making a service or an operation that resolve that counting problem if it's going to take that time. We need something that can be resolved at real time at least, or for the least part at a time that is manageable. So here with the mathematical discoveries that we have in sums, asymptotics, or on cardinality, this problem becomes from a complexity of that is linear to the scale, for example, an ON or an ON square to a O1, where it is manageable to be done at not just real time, but at the milliseconds of one operation. So that's how different or how much advantages to use uh, the mathematical backdoor that I'm discussing here. So an implementation would be in sums and asymptotics. So in sums can be transformed to a closed forms. And this closed form can be calculated through one operation. And an example would be the sum of I that can be scaled from 1 to an n number that could, let's say, very high number. It's really hard to calculate. And if you're gonna, it's not hard with normal numbers, but with high scale, it's insufficient for the computer to calculate. For humans, it's not the same case. I think it's good to get to the case that is impossible. But in this case, we just want to talk about computers here. So I'm just gonna reflect it on computation. So as I said, it's gonna be inefficient, but we have theories that transform these sums to a closed form. In this case, it's this sum equals to n times n plus 1 division by 2. So you only need to calculate this with one operation and you're done. Unfortunately, not all the sums have this type of closed form, so we need to have a resolution for those too. And a way to do it is to calculate an approximation for them. These approximations can be really close to the accurate results since they're floats or double numbers. It's really hard to get the exact number. So, but we can get to an accurate value, and the way to do that is through the this inequality theorem that we have. I'm not sure if inequality is the right word. I only know it in French. But as you can see here, we are bounding the sum S with two values or two functions that are the integral of that sum. And once you calculate that those boundaries and you scale those numbers to the infinity, then you're gonna have a pretty close value to the accurate results. And there is sometimes, as I said, when the scale in here goes to infinity, we're gonna imply asymptotics also. And this imply not only to the converged sums or converged countings, but also to the ones that are divergent. And for the divergent ones, we're not really searching for the value here, but we are searching an idea about the value. For example, we want to compare two functions. If one function is um superior than the other, like bounded by it in a superior way. And a French word would say majoré or minoré. But yeah, you got my point. So we're most of the time we need to sacrifice some stuff to stay in a efficient way to resolve the things, but get the minimum information that we need. Example here, we don't need to know the value. We only need to know an idea about the value. And these asymptotic solutions are really useful when we try to calculate the complexity of your computation that we are trying to resolve and be efficient with math at the first place. Cardinality is the same thing. It goes with the from counting numbers, but rather counting elements in a set to make a subset of that from that set. And if you're gonna do it in the classical way through going through each element, then it's gonna scale linearly with with the set that you have. So it's gonna be an complexity of an n, O(n). But that's not the case. If you're gonna have get those subsets with the consideration of the sequence of those elements or the duplication of them, then it's going to get to a quadratic scale for the resolution of that set. So, however, with the mathematical findings in cardinality, this logic can conclude to one operation also, where we can have calculate them through the cardinality of the elements that have through all that set and the elements that you want from that set. Well, the choice of that or the choice of that number depend on the logical conditions that you want to use to take the elements that you want on the subset. But that can be concluded just in the reflection of the design of that computation and can be deduced dynamically in the algorithm that you're making. So yeah, that's an this is not an idea, new idea that I'm sharing here in this video, but I'm just sharing an implication of the previous idea that I shared in the old video, the previous one. And I hope I explained it well. And yeah, thank you for watching.